now we're going to look at the graphs of these functions of two independent variables. The graph will be all the points of the form xyz, which are in R3, so in the three-dimensional coordinate system. So all the points xyz that satisfy the function z equal f of xy. So remember, when you graph functions in two dimensions, you had y equal f of x, so that your domain was the set of all x's, and then you got y values for each x, so the graph was actually the set of all points xy that satisfied y equal f of x. So we're just adding one more independent variable. So our domain then is actually the xy plane. So here's our domain. For each point in the xy plane that's in the domain of the function, there will be some z value up here corresponding to it. So for each xy, there should be a unique z if this actually is a function. So the relation, if you have the equation written in this form where it's implicit form, that's not the function notation. So this will be a function if every line parallel to the z-axis intersects the graph of f at most once. In other words, for each point xy in the xy plane in the domain, there will be a unique z value. And so that means that it's passing the vertical line test. So the vertical lines are parallel to the z-axis. So every vertical line parallel to the z-axis needs to hit that surface once, at most once, for each point in the xy plane. So if it hits it, has more than one place that it intersects the surface, then it will not be a function. So let's find the domain and range of each of these functions and then sketch the graph. First, this function, f of xy equal 2x plus 3y minus 12. The domain, which is determined by figuring out which values for x and y can be put in so that we get a unique z value. Remember, z is the same thing as f of xy. You see that this is just a polynomial in x and y on the right side. So that means that we can put any possible xy value into this function and we'll get a unique z value. So the domain is actually all of R2, or in set notation, it would be the ordered pair of xy's. Indicate that it's a point. You have to have an x and a y value to plug into the domain, such that x and y are real numbers. So x is a real number, or we can say x and y, x comma y are elements of the real numbers. So that's our domain. Now the range is the possible z values. Now, if you try to consider what possible values will you get for z, it's easier to realize that by looking at this equation. If I rewrote this as z equal 2x plus 3y minus 12, then I could rewrite this as 2x plus 3y minus z equal to 12. And hopefully you recognize that form as a plane. So this will be a plane in the three-dimensional coordinate system. Remember, the normal vector is those coefficients. It's the vector 2, 3, negative 1, or any multiple of that. Okay, so we have a plane. So imagine the plane. It's not parallel to any of the axes. So we've got some plane. Let's go ahead and get the graph of it. We can easily graph it by finding the intercepts. The x-intercepts you get by letting y and z both be 0. So we would have 0 equal to 2x plus 0 minus 12. So we would have that x is equal to 6. The y-intercept we get by letting the x and the z be 0. So that means that y would be equal to 4. And then the z-intercept, we let the x and the y be 0. So z equal negative 12, somewhere down here. So the plane would have orientation something like that. So now what possible z values? Imagine that plane that's slanted like that. Will every possible z value be achieved? Will there be some xy in the xy plane that would have that z value? Now, because this plane goes off infinite in every direction, the range here is actually going to be all possible z values. So we'd say it's the set of all real numbers, z, or and you can use any letter here. It doesn't matter if it's z or x or y or whatever. This is just emphasizing that it's a single number. Z equal, r equal the set of all z, so that z is a real number. That means all the possible real numbers, or you could just say the range is actually the real numbers. Okay, so now the next equation. I want the domain. What possible points can I put in, or values for x and y, so that you will have a z value defined? Well, you can put any x and y values in and you will get a unique z value. So this is a function. Well, of course, it's in function notation, and the domain is also all real numbers. So it's the set of all, because you have to have an x and a y for the domain. It's the set of all ordered pairs x, y, so that x and y are real numbers. So either of these two, this indicates all points, all ordered pairs, and this indicates all ordered pairs where each number itself is a real number. So now let's look at the equation. Z equal x squared plus y squared to have an understanding of the graph. Notice that if z is 0, which is the points in the xy plane, we get just a single point, 0, 0, 0. If x or y are 0, so if we're talking about the xz trace, that means that y is 0, then we have the equation z equal to x squared. If we're looking at the see, the xy trace was just a single point, so now we want the yz trace. So let y and z be 0, or let the x be 0, and you've got z equal to y squared, which is also a parabola. So we have a parabola in this direction and in the other plane. And now if we were looking at planes parallel to the xy plane, so let's say we looked at z equal to 2, then we would have x squared plus y squared equal to 2. Or if z was 5, x squared plus y squared equal to 5. We're going to have circles. Okay, so what we've got is we've got a paraboloid here. Okay, the range. Well, you can see what possible z values you have, because if you let z be any negative number here, there would be no solution to x squared plus y squared being a negative number. So the range is only real numbers that are greater than or equal to 0. So I could say the set of all z such that z is greater than or equal to 0. Or I could use a set notation. It would be all the values from 0 to infinity. Okay, so z is an element of this interval. Or you could just say z greater than or equal to 0. Okay, so now the last one here. Let's look at the domain. What possible x and y's can I put in here? Now, we have to deal with the radical, but because it's pluses, even if you put negative numbers in here, well, when you put negative numbers in, these two terms will be positive, the x squared and the y squared will be positive, but we're adding them. So no matter what values you put in for x and y, 1 plus x squared plus y squared is always going to be greater than or equal to 0. It's always going to be a positive number, so we can take the square root. So that's always great. Actually, it's always greater than or equal to 1. The smallest this could ever be would be 1 when x and y are both 0. So the domain is all possible ordered pairs, the set of all x, y, so that x and y are real numbers. Or you could simply say it's R2. That's ordered pairs. The range, what possible z values can we get here? Z is the square root of 1 plus x squared plus y squared, but we know that that's greater than or equal to 1. And we can see that z is always positive since there's a positive number in front of the radical, and we know radicals are always defined to be positive. So the only possible z values will be the bigger than or equal to the square root of 1. So we know that the range is the set of all z's so that z is greater than or equal to 1. So let's see if we can figure out what the graph of this looks like. The domain's all real numbers. And now let's look at the equation. Z equal the square root of 1 plus x squared plus y squared, and see if this helps us to see the graph a little better. Square both sides. Z squared equal 1 plus x squared plus y squared. That is z minus x squared minus y squared equal to 1. Now notice if x is 0, we would have a hyperbola. Wait. The z, okay, yeah, I didn't put the z squared here. Okay, if x was 0 or if y was 0, which means we're looking at the yz trace or the xz trace, we would have hyperbolas. If the x and the y were both 0, or if the z were 0, we'd actually have x squared plus y squared equal to -1, which is not possible. So z can't be 0. So since the range here is that z values have to be greater than or equal to 1, if you graph this, we do have those hyperbolas. You know, if you look at the traces, the xy or the xz or the yz trace. But this is a hyperboloid of 2 sheets, so that part of the graph is up here above the xy plane. The other part would be at the bottom, but because this is just a positive, when we solve for z, we're only taking those positive values. So that lower half of the hyperboloid of 2 sheets would actually be, not included in this function. It wouldn't be a function if you actually had both halves. But this is function notation, and it's taking just the top half of that hyperboloid of 2 sheets.